polar curves are just a special case of parametric curves, which you would have talked about. Well, you talked about them a little bit in Calc 3 under parametric curves, and then you spent all that chapter 13 stuff with space curves and all that. And so this is sort of building on some of those concepts. If you think about this as a new thing, it'll drive you nuts. If you think about it as just a special case of parametric curves and space curves, it should be pretty straightforward. And so just kind of starting at the top, to find the tangent line to a polar curve, we regard theta as a parameter and write the parametric equations as follows. So you have x as a function of r, or x is equal to r cosine, y is equal to r sine. And you got to remember this formula. Let me see. Got to remember this formula where from Calc 3, where we had the dy dx was equal to dy dt over dx dt. This is the key formula. And so we can figure out if x is equal to r cosine, then find out what is dx dt, or in this case, dx d theta, the dx d theta. We need to find dy dt, or in this case, it'll be dy d theta. And so you go through, use the product rule, and you find this formula. So here's your key formula. It's coming out of the product rule. You can see that product rule happening here. U times V equals U prime V plus U times V prime. And you do it in the numerator, you do it in the denominator. It's just a formula. It's not magical. It just comes from the parametric stuff from above. Questions, or are you ready to apply it? Cool. And if you haven't found it, again, you can give the little thumbs up under the reactions, or I think that there's a place, if you hit the participant button, you can raise your hand if you have a question, or you can say slow down or speed up, things along those lines. Okay, so continuing on down, we'll work through some by hand, but these first ones are pretty straightforward, so I'm just going to kind of just show it. So we want to find the slope of the tangent line to r equals 1 minus cosine theta at theta. So we're going to just end up with a function. And so we're just going to use the formula from above. So we need our r. It's 1 minus cosine, that was given. Dr d theta is sine theta. And then we just sort of plug and play. So our formula was as follows: dy dx equals, and then we have the quotient from above. So this is the same formula above. And we just plug the various things in there. So the r primes get replaced by sine thetas. The r's get replaced by 1 minus cosines. Do some basic trig, simplify, et cetera, et cetera. And at the end of the day, we have this formula that dy dx is equal to cosine minus cosine 2 theta over sine 2 theta minus sine theta. It's just kind of a little bit of a plug and chuggy type of situation. So it might lead you to ask, what in the world does that mean? Like, what does it represent? And so I'd like to follow the sticker and check out manipulate number 12.35. So this would be straight out of the ebook, which is, yeah, super cool, super powerful. So let's see if we can pull that up. So I'm opening up the Wolfram player, that I asked all of you to download. And I better clear all my drawings. I downloaded these animations in advance. They'll be within your homework assignments so that you can find them easily. They're also in the ebook, and they just give you a chance to play with these things yourselves. Calculus is very intuitive, and so the more you can see it and touch it and taste it and feel it, I think the easier it is to understand calculus. So here's the cardioid that we were messing around with, and our question asked us to find to find the tangent, slopes of the tangents. And so, for example, we find that if theta is equal to negative 2 pi over 3, then the slope is 0. And so you could probably pretty easily guess the types of questions that would come out in a homework assignment. They'd be questions like, gee, find where the slope is 0, find where the slope is undefined, you know, those kinds of questions. And you can use those slopes to graph and kind of all the old things that you did in pre-calculus. So it's nothing new, but this is a nice animation because it connects the cardioid that you're playing with, the actual graph, and the slopes. And remember that function that we found, let's see if I can pull it up, that this function that we found, it gives you the slope. And so you would take the theta, and if you took a theta, maybe pi over 2, and you put it into the original function, it would tell you where the point is. And then if you took that same theta of pi over 2 and you put it into here, it would give you the slope at that particular point. So we just covered, we just sort of jumped in. You guys have been on break, and we just started doing parametric curves and derivatives and polar graphing, and things are going like crazy. I was pretty excited about this. Here we are talking about polar stuff, and I discovered that I have snowflake stickers. That was pretty rad. So we need to derive a formula for an area, like think about the area under the curve, except for we're no longer an area under the curve world. And so rather than going through all this stuff, I want to show you the animation, but I need to remind you of a formula. So recall that the area of a sector of a circle is the area equals 1/2 r squared theta. What do you mean recall? Like, if you're anything like me, I probably wouldn't recall that. And so for me, I just remember this by remembering that the area of a circle is pi r squared. And so this would be what happens if your theta was equal to 2 pi if you were going all the way around. And so this formula for the area of a circle is simply coming from, for the area of the sector is just proportional to the area of a full circle. So don't think about it as magical. It's something that you know. It's something that you could all figure out. All right. Okay, so rather than spending time walking through this complicated derivation, let's go and let's look at the manipulate and understand what's going on. Where'd it go? I want to open. Yep. All right. Is that legible to everyone? So whereas before, in our old calculus world, we would do the area between A and B, and that A was on the left and B was on the right. Now we're going to go between alpha and beta. So alpha is telling us something about the lower angle, and beta is going to tell us something about the upper angle. And we're going to be finding this region. I think it's pink. It's a little hard to see the color. So how do we do it? Well, it's just like in Calc 2. You divide it into a whole bunch of regions, and instead of approximating with rectangles like we did before, now we're going to approximate with a whole bunch of sectors of circles. And shockingly enough, if we increase the number of sectors, then we're going to get closer and closer to the exact area. And if we add up enough of them, then, in the limit, we will get the exact area. So you've got the area of each, one individual circle, or one individual sector. I keep saying circle. One individual sector. You add up all those individual areas. That gives you an approximate area. Take the limit, and you get the exact area. So from that derivation, I hope you can see why we would have the area equaling the integral from a to b of 1/2 r squared d theta. The 1/2 r squared d theta is the area of each sector, and the integral tells us we're taking an infinite number of sectors with infinitesimal, theta width. So I just wanted to do a quick tutorial to demonstrate how to use the graphing calculator to graph in polar coordinates. So here I have my graphing calculator emulator. I'm going to start by making sure the mode is correct. So I'm going to go to mode, make sure that we are in radians, go down to function and highlight polar. This changes my y equals so that it looks like R1, R2, R3 instead of Y1, Y2, and Y3. I'm going to graph the polar rows. 2 cosine of 2 theta. And we can graph this in the standard window, zoom 6. This is a little far out, so we could zoom in, of course. Nice, pretty picture. I want to show you just how to see just this one part and verify that your limits of integration are correct. So one way of doing that is to limit the theta range in your window. So we think that this is theta equals 0 and this is theta equals pi over 4. Let's just verify that using our window. So my theta minimum is 0. My theta maximum is going to be pi divided by 4. And now we can go graph again. And sure enough, we just get that half of a petal of the polar rows. And that verified that our limits are going to be accurate. So when we find our area, we're set to jet. It can also be really helpful when you're trying to verify where polar curves intersect. That's it. That's all there is to know about graphing polar functions on your Texan friend. So again, we're going to take advantage of symmetry and say we can find the area of 1/2 of a petal and then multiply that area by 8, and that will give us our total area. So if we're going to find this area, we need to know the limits of integration. So step two is to find those limits of integration. And so you'll notice that at this point, I mean, you might be able to guess what they are, but at this point, the r is equal to 2. And so I want to know when 2 is equal to 2 cosine 2 theta. I can solve through, and that would be at 0. And then here, this would be when 0 is equal to r, or 0 is equal to 2 cosine 2 theta. Solve through, and I get theta equals pi over 4. There's actually an infinite number of solutions, but the one that we care about is the first one, which is part of why we wanted to focus in on that very first quadrant-y part. So we graph the function, draw what we're after, find our limits of integration, and then we set up and evaluate an integral. So the area is equal to 8 times the integral from 0 to pi over 4 of 1/2 the radius, which is 2 cosine 2 theta, quantity squared, all integrated with respect to theta. Notice 2 squared is 4 times 8 divided by 2 is 16. Integral from 0 to pi over 4 of cosine squared 2 theta with respect to theta. In order to integrate the cosine squared, we need to use a half angle identity. So this will be 16 times the integral from 0 to pi over 4 of 1 plus the cosine of the original angle squared. So instead of 2 theta, we'll have 4 theta, twice the original angle, quantity over 2 d theta. The 2 in the denominator, or the 1/2, can come out, the integral, leaving us with 8 times the integral 0 to pi over 4 of 1 plus cosine 4 theta d theta, which is 8 times theta plus 1 over 4 sine 4 theta from 0 to pi over 4. Good news, at 0, theta and sine 4 theta both evaluate to 0. And at pi over 4, 4 times pi over 4 would be pi, or sine of pi would also be 0. So we're simply left with 8 times pi over 4, which is 2 pi, which is the area of the polar rows. All right, let's look at a manipulate and make sure you're tracking what's going on in terms of this process. Ooh, was I? Oh. I'm learning about my technology. Okay. All right. Okay, so here's our third manipulate. So here's the polar rows, and you can see that as we go along, we're just simply going to be sweeping out. It's going to be sweep out over and over, or like it would repeat over and over and over and over again to go around. But what we want to do is just focus in on that first chunk right here from 0 to pi over 4. And when we do that, we find 1/8 of the total area, multiply by 8, and you get the whole area for the thing. So pretty straightforward. The picture's easy. The pictures are pretty and easy. The main thing is you end up having to use a few trig identities along the way. So nothing too crazy. Questions or keep going? Give me a thumbs up, a pause. How about some light?
Quick question.
Go ahead.
So could you remind me how you got the limits again for that previous curve?
Yeah, totally. Thanks for asking.
All right.
So to find the limits of integration, the first thing I did was I looked at the first thing I did was I sketched the curve. And so I looked for where is the curve, like what are the angles what are the points that I care about? And so I'm trying to find this area here. And so the boundary markers of that would be at this point and also at the origin. And so at the point on the right, what would be the R value? This would be where R equals, go ahead, Titus.
2?
Yeah, 2, exactly. And then at the origin, R would equal 0, right? So I can look at the picture, and the picture tells me what R values I'm looking for. And then I can go down below. Nice. I can go down below, and here's 0 representing the origin equal to the function. Here's 2 representing that right-hand point equal to the function. And so 0 equals 2 cosine, divide by 2. And then I'm just asking when is cosine equal to 0, and that would be at pi over, well, that would be, when is cosine 2 theta equal to 0, and that would be at pi over 4. Does that answer your question, or does that just generate more questions?
It answers it. Thanks.
Yeah, so we're using our old unit circle knowledge to try to fill in some of those values pretty quickly. And if you want, I'd be happy to meet or connect and talk about solving trig equations as well.
Sure. Thanks.
No problem. Good question. Any other questions before we go on?
what does the k pi over 2 and then the 2k pi at the end of those limits of integration parts represent?
The 2k pi and the k pi over 2 represent the fact that there's actually an infinite number of solutions to these equations. So, and maybe it's easier to see on the 2 here. So think about how the curve is sketched out. So if you were to graph it, it's theta equals 0, and then the curve kind of sweeps around, and then it gets back here at 2 pi, and then it keeps going. I think I got out of order. And then we're here at 4 pi, and then we keep going around, and we're here at 6 pi. So the 2k pi would be saying 0 plus 2 times 0 pi, 2 times 1 pi, 2 times 2 pi, 2 times 3 pi, or 2 times negative 5 pi, 2 times negative 6 pi. So it's all the integer multiples of 2 pi. Does that make sense on the 0, on the 2k pi?
Yeah, thank you.
And then the k times pi over 2 is because we're going through the origin a lot of times, so that's why it's happening so much more often.
Okay.
Other questions?
All right. Okay. So I'm back to that previous example. So you said the 0 and 2 cosine 2 theta just because they both have the same y value, right? Which is 0, right?
At this point, they would have the same x and y value.
Okay.
Yeah, and here they would, at this other point, they would have the same x and y value. So here the x value would be 2, the y value would be 0. The two things are gonna overlap or intersect.
All right. Gotcha.
Yeah, and I think that the next example might make that a little bit clearer. So maybe let's move on and see whether this helps, okay?
Sure.
So the next question, I just want to focus on the process and also the question that you've been asking. So here we want to find the area of the region that lies inside the circle r equals 1 and outside the cardioid r equals 1 plus cosine theta. So step 1 is going to be the same, sketch the region. And so I sketch out my circle and I sketch out my cardioid. Remember, cardioid is like heart. And we recognize we want the region that is outside the cardioid. So that's all this stuff, but inside the circle. So this is the overlapped region that we're after. And so we can again see symmetry. And so we're going to just look for the area of one of these little chunks and multiply by 2, and that will give us our total area. So if we've sketched our region, we see what we're trying to find, and now we need to find the limits of integration in step 2. And so those limits of integration are going to be kind of the key points. So we're after this region right here. And so you can see kind of the key points are right here at the origin and up at the top. And remember that we describe points by thetas, not by x's and y's. So all these points along the negative x-axis, these all have the same theta value of theta equal to pi. And the point at the top has where the circle intersects with the cardioid would be where theta equals pi over 2. And so by graphing, we can just simply see what the two theta values are. We can find those theta values algebraically by saying this top value would be where the cardioid, r equals 1 plus cosine, equals the circle, r equals 1. So here's the cardioid, r equals 1 plus cosine. Here's the circle, r equals 1. And I can set those equal to each other. And that will tell me the theta value where the two intersect. And so they're going to intersect when 0 is equals a cosine, which is when theta equals pi over 2 plus k pi. you might say, well, what's up with the k pi in this case? Well, the k pi is because the two intersect up here at pi over 2, but they also intersect down here at 3 pi over 2. And they intersect again at 5 pi over 2 and 7 pi over 2, et cetera, et cetera. So the pi over 2 gives us one of the intersection points. The other intersection point we want is where we go through the origin. This would be, we could have also looked for where r equals 1 out here, but it's kind of the same thing. So we're going to look for the origin. So we set the cardioid, r equals 1 plus cosine theta, equal to 0. This is like r equals 0. It represents the origin or the pole. And again, we solve. -1 equals cosine. That would be when theta equals pi plus 2k pi. And what we care about is that first intersection point. So thinking about your question, Melissa, thinking about your question, Titus, does it make a little bit more sense how we found those intersection points and those limits of integration?
Yeah.
Hey, Dusty,
Yeah,
I got a question.
go ahead, Jay.
So, is it necessary to write like this stuff, k pi to k pi, or just we can write pi over 2 and 3 pi over 2?
I think you're okay writing just the pi over 2 and the pi. I don't think you need to list them all out. The mathematician in me wants to be a little bit more precise, but I think for the sake of homework, for the sake of getting where we're trying to go in the class, I think what you wrote in yellow would be perfect. When you go through and you work it, there's a few questions that are a little bit more subtle, and so I'm guessing some of you are going to be stopping by office hour asking for some more subtle questions later, but I'm okay without the k-pi's in the short term. Does that answer your question?
Oh yeah.
Cool.
Oh
Good
yeah.
question.
And like why we are using this formula?
Which
F of
formula?
theta square d theta.
Oh, the 1/2 r squared d theta.
Yeah. Yeah, this one, I think, yeah.
Oh, we talked about that at the beginning of the class. This 1/2.
Oh yeah, got you. Okay.
This 1/2 r squared represents the area of a sector of a circle.
Oh, sector.
Yeah, and it's a pretty straightforward thing. Look back on page, right at the top of page, I think 5 or 6 or something like that. You'll see a little sector of a circle, and it'll show up really easily. Good. Any other questions?
Yeah. Nope, that's it. Thanks.
No problem. Thanks for asking. Cool. So from that point on, we're going to set up the integral and we're going to evaluate. And I don't want to work through it because you guys have all integrated 1,000 times. So again, we're going to find I'm going to just focus in on the part of the region, so half of the region we care about. And so we have half circle, and then we're going to subtract out the yellow part, set up the integrals, do a little bit of calculus and trig, and it all works out. Does that, I mean, there's some work to do, but does that make sense? Give me a thumbs up if you're good to go, like the kitten. Cool. Looks good. All right. I'm not going to go to this manipulate because it's very similar to the previous one, which is to say not terribly exciting. So let's go on and I think talk about our last topic. We just have a few minutes left. And so the last topic is, again, a straight up extension of what you did with parametric equations. And so you might remember that if you wanted to find the arc length with parametric equations, you'd find the integral from t equals a to t equals b, and then you'd have like a Pythagorean theorem thing going on. So dx dt squared plus dy dt squared all under the radical. Hoping that rings a bell. It's just straight up extension of the Pythagorean theorem. And so we did that before, and now instead of having t, we've got theta, and we've got formulas for x of theta and y of theta. So remember, our x is our cosine, our y is our sine. You work through it all using this formula. And so here's the stuff under the radical, the dx d theta quantity squared plus dy d theta quantity squared. Plug all that stuff in, and this is going to blow your mind. You're going to be like, oh, I did not see that coming at all. Like, right in here, you'll see, where'd it go? Where'd that r squared? I lost it. Pardon me. You work through it all, and you'll see here like an a squared minus 2ab, and then plus a b squared, and that a squared minus 2ab, that's our perfect square. No, sorry, Dustin. My bad. I'm sorry. I'm sorry. That one and that one, that's your r squared right here. And then here's a minus, and here's a plus. Those ones die. Here's another cosine squared and sine squared, which is this term. And so your, pardon me for that, your dx d theta quantity squared plus dy d theta quantity squared is just simplifies to dr d theta quantity squared plus r squared. Stick it under the radical and you get that the arc length is equal to the root of r squared plus dr d theta quantity squared, all d theta. It looks like another formula to memorize, but the reality is it's just a straight up extension of the formula you already had for finding the arc length of a parametric curve. Makes sense? Why don't you give me a thumbs up or thumbs down? Nice. Cool. So the nice part about formulas is we get to use them. So last but not least, in this last example, we can find the length of the cardioid. We've got r, we've got dr d theta. We just kind of plug and chug. Stick the stuff in. I decided to use symmetry. Again, this is the same cardioid as earlier, so I'm kind of doubling my size. So I'm going 0 to pi instead of 0 to 2 pi, taking advantage of the symmetry. Stick everything in. Shockingly enough, Pythagorean identity comes through. Woohoo! Basic trig, integrate, and you get a number out the back end. That's the point is not the integration. The point of the example isn't the integration. The point of the example is that that once you have that formula, you can set it up, and then it takes this question that's a Calc 4 multivariable calculus polar calculus question and turns it back into a Calc 2 just plug and chug type of scenario. So what did we work through? We talked about how to find the slopes of tangents for polar curves. We looked at how to find the area of polar regions, and we also looked at how to find the arc length of a polar curve. None of this stuff is new. It's just all a special case of finding the slope and the area and the arc length of a parametric curve.